Hey, hi, everybody. So we're going to get started. Welcome to the first TAP Meet Yourself and first colloquium of the year. My name is Gertina Bessela. I'm a professor in the astronomy department and chair of the theoretical astrophysics program. And we have an amazing lineup of students coming from our TAP departments who are going to be talking about the fantastic theoretical research that they're working on. Before we get into this, I wanted to just give a few announcements. So here's our lineup for the TAP colloquium for this year. September 22nd, we're going to have Jackie Kobayashi to start us off. And so we really encourage students and postdocs to sign up for lunch with the speakers. We're trying to make sure that there's a dedicated time for students and postdocs to meet with the speakers. So just look out for the sign up sheets then, or sign up links. We are also offering travel grants. A little bit different this year. It's going to be offered twice this year because we're changing the cadence to match up with the fiscal year. So the first one is going to be coming up soon. We're going to have applications due by October 15th. And this is going to be for the fall and spring travel. And then in the spring, we're going to have another cycle for another. So this is for $1,000 for travel, for going to, this could be to present a paper, it could be present a poster. It could also be for a workshop that you need to build your skill sets. So there's a variety of different reasons. This is open to all students who are working with TAP faculty. And we also have a lectureship series and initiative series that goes on throughout the year. These are more focused discussions on certain topics that are interdisciplinary, so interest to multiple departments. So for example, our computation and data initiative, this is important for all three of our departments, physics, astronomy, and planetary science. There's going to be a TAP lectureship and computational workshop. So we're really focusing on having opportunities for students and postdocs to learn computational skills. And what this means is it's probably going to be a pretty advanced code specific to this area. Another example here is what Dahlia and Joanna are both going to do will be some high level work often involving machine learning or other advanced AI techniques. And so it's an opportunity for you to advance your skill sets. It's open to faculty and staff as well. So because these are all pretty high level. The Planet Formation Initiative is also going to have folks visiting alongside also computational workshops, right? So these are skill sets that you can learn for a particular code to advance your research. So we're making sure that these folks are coming in. It's coming for actually more than just a day. It's not just one talk. They're here for about a week. So you have time to meet with them, interact with them, get to know them, build collaborations, and then utilize their codes. Planetary Atmospheres is also going to have an initiative this semester. So we have 3 different units: planet formation, planet atmospheres, and computational data this semester. All of them have computational workshops associated with them this semester, and there's going to be another set coming in the spring. Oh, and cosmology. Don't forget cosmology. So there's 4 actually. A new lectureship as well, which we're going to be setting up soon by Robbie. Yep, that's the first slide. So we're going to get started. I'm going to pass it over to Mathieu to introduce the speaker.
No.
Right, slide and answer.
Oh, well, I think that we'll go to the speaker. So the first speaker that we have today is Chaucer Langbert. Where you hear this. And this is about the slides. I know you're fine, but you're 4 minutes.
Can everyone hear me okay? Perfect. Hi, I'm Chaucer. I'm one of the resident 3rd-year grad students here at LPL. And today I'm going to be talking a little bit about my research. So the main overarching question that I'm hoping to answer is, how do climate feedbacks affect both the diversity and the habitability of Earth-like worlds? Now, for those who may not be as aware, a feedback is just a process that responds to changes in climate. So, for example, there are 2 types. There are both stabilizing and destabilizing feedback. So in the case of a stabilizing feedback, if you had some perturbation to the climate, you would expect that feedback to operate it to bring it back to equilibrium. Now on Earth, we have 3 main feedbacks that are used to describe Earth's long-term behavior. And that's these 3 feedbacks here at the top. There are other feedbacks that also operate on Earth, but they're relatively weak and aren't necessarily really to explain Earth's mean long-term climate behavior. And so these are used to define the habitable zone. the question I'm interested in is, given that we know that exoplanets are a diverse bunch of planets, can we expect this same feedback configuration to be operating on other Earth-like worlds? So what I've done in my modeling work is incorporated a model with those three feedbacks that I showed earlier that are known to operate here on Earth, and I incorporated a fourth feedback. It's a general feedback. The equations don't matter too much here, other than to say we have a coupled set of ordinary differential equations that track temperature T, the partial pressure of carbon dioxide, so how much carbon dioxide does your atmosphere have, and then this fourth feedback term F, which isn't meant to necessarily say anything about a specific process, but rather be general because we don't fully understand the diversity of Earth. And so what we do is we run many simulations that solve these equations, but tune each of the different parameters. So we can see over 5 billion years how Earth-like worlds might respond to having an additional fourth feedback. To do this, I ran tens of thousands of simulations on the University of Arizona HPC, which was fantastic because I could run all of these jobs in parallel to one another, so I didn't have to wait for them to run one at a time. And what this allowed me to do is I got to randomly configure the fourth feedback strength, that's the important F, and then a couple of other relevant parameters to the model. And once I randomly sampled this 10,000 times, I could integrate over 5 billion years, classify the resulting behaviors, and then do some further analysis. So generally from these 10,000 simulations, I found four main types of behaviors. The first one I'll point out is this second row here. So here we have the feedback configuration. The fourth feedback is this purple one. So it changes in both time scale and the temperature at which it acts. But what we see here is temperature is in blue and it's a flat line. It's not terribly interesting to look at. And carbon dioxide as well, that remains at a level value. This is something we see here on Earth, which is that Earth has been warm and habitable for the most part over its 4.5 billion year lifetime. But we see three other behaviors as well. The first one being out of bounds. So what this can look like is a runaway, something like Venus perhaps, or even a runaway snowball, something like Mars, which is incredibly cold. What you can see here is something called a phase space here on the right. So here we're plotting the carbon dioxide concentration as a function of temperature. And over time, we can see the temperature and carbon dioxide concentrations fall off the plot. And it does this only in a couple of million years. What we also see is something called a limit cycle. So what we see is this point right here is a snowball point where the entire planet would be covered in ice. And as carbon dioxide builds up, it can eventually escape the snowball and become a warm point, something like we have like Earth here today. And once that happens, you lose carbon dioxide and you can actually go back into the snowball. So this is something that's cyclical and regular. But the introduction of a fourth feedback now introduces a new behavior that wasn't seen with the three feedback model, and that's something called chaos. So what that means is the temperature and carbon dioxide values remain bounded to a certain area, but actually predicting where it's going to be at any given time is incredibly hard to do. So you can see it's relatively compact, but if you zoom in, there are some oscillations in there, but they're not nearly as regular as these limit cycle oscillations. So we can break out these behaviors for all 10,000 simulations. So here on the left, I've broken the feedback strength into bins. So each column here is a binned feedback strength. And what we see is that these negative feedbacks, these are stabilizing feedbacks. And what we see is as they get stronger, we see warm fixed points. These are the pink ones, which are Earth-like. But as we go to stronger and stronger feedbacks, we see that these purple out of bounds points take up more of the bin. So what that tells us is that you tend to see more runaway climates, either snowball or hothouse states, as you have stronger both stabilizing and destabilizing feedbacks. And then kind of up here, you'll see a little bit of orange and dark purple, and these are the limit cycles in chaotic behaviors. So what that means is while these are rare, they still do occur. So even if you have a feedback that you think is stabilizing, you can actually induce behaviors that cause your planet to be less habitable over time. Here on the right, what I'm showing is the fraction of time that each run spends in temperate surface conditions. So with a water ocean that's can support life as we know it here on Earth. And what we see is another way of looking at this trend, which is Earth, as we know, is essentially stable over its entire lifetime. But as we increase the feedback strength in either direction, we see that a stable, warm climate that's habitable is less likely to occur. Okay, we talked about a lot, but I'll sum it up very quickly. What we see when we add a fourth feedback to an Earth-like climate system is that we have expanded dynamics. So we don't have just warm states or just snowball states, but now we expand into limit cycles and even chaotic behaviors. What we also find is that Earth might be rarer than we thought. So I guess fingers crossed, we hope that fourth feedbacks are rare, but if they aren't, that doesn't bode so well for our search for life. And this has implications for future surveys, because if we wanted to find Earth-like worlds, we would have to look at dozens to maybe even hundreds of worlds to identify Earth-like climates. Thank you.
Great talk. The second parameter that you were looking at was not only the strength, but also the time scale over which the feedbacks were occurring.
Yes.
Do you have a similar kind of distribution and an understanding of the importance of that as a feedback?
Yes. Something interesting we found is chaotic behaviors actually happen near the ice albedo feedback. So I didn't talk about this too much, but the ice albedo feedback is a destabilizing feedback. When an ice sheet grows, it becomes more reflective, cools down the temperature, and so that sort of thing can be a runaway effect. If you have a fourth feedback that acts near the same temperature range as the freezing point of water, they can actually interact with one another. And so that's where you get chaotic behaviors, where you have this destabilizing ice albedo effect, but now you have another effect that's somehow stabilizing it, and that can actually lead to chaos. So that's one interesting trend having to do with the temperature at which the feedback acts. But I'm sad I didn't include that slide, but that's one example. But as for out of bounds and that sort of behavior, that's all over the map.
Interest of time. Thank you, Chaucer again. University.
How's that sound? Great. So hi everyone. I'm Avery Bailey. I'm a postdoc and steward, and I'm primarily interested in questions about planet formation. And so today I'm going to talk to you about some work I've done with Caitlin Cratter and Andrew Uden on how we can extend sort of the theory of Bondi accretion to the cold environments in which planets form. So to get started, I'll just sort of kind of review what Bondi accretion is. Most of you have probably seen this at one point or another. But back in 1952, Hermann Bondi was looking for steady state accretion solutions for massive objects. And under the assumption of spherical symmetry, as well as some adiabatic equation of energetics, he found this set of accretion solutions. In particular, the one highlighted in yellow is the so-called Bondi accretion solution. And the main idea is that it starts from zero velocity at infinity. As you move inwards, you get the subsonic transitioning to supersonic flow, and then it passes through the sonic point that lines up with Mach number equals 1. So that's a fundamental accretion solution. And he also showed that it really only depends on a single dimensional parameter. That parameter is the adiabatic index gamma. It's nice enough, though, that the mass accretion rate only depends weakly on this gamma parameter. So we write out sort of the Bondi accretion rate. It really only depends on the object's mass and then properties of the background medium. So the background mass density, and then the background sound speed. Okay, so how does this apply particularly to giant planet formation? Well, if we imagine sort of how we think we formed Jupiter, we take a rocky core and we stick it in some protoplanetary disk. As this core gets more massive, it begins to bind an envelope. And this envelope at low mass, at least, is in roughly hydrostatic equilibrium. In this phase, the only way to accrete and grow is by cooling, and in particular Kelvin-Helmholtz light cooling. And so this phase of planetary growth lasts roughly 1 million years. But once that envelope becomes so massive as to exceed the core mass, the cooling becomes much more rapid, and we enter this phase of so-called runaway accretion. In this particular phase, the accretion is no longer quasi-static, but rather hydrodynamic, and so we can hope to apply something that looks more like Bondi accretion, and that we just have material falling freely from the protoplanetary disk onto our planet itself. And in particular, I've also added an accretion shock here, which is to imply that this planet and the associated accretion shock can be quite hot. And so you might expect that as this hot planet radiates, it can perturb the accretion flow itself and potentially change the character of the accretion solution. So that brings me to my main point, which is that current formation models treat runaway accretion generally in sort of the 1952 prescription of Bondi. That is to say, they're adiabatic. But really, we should be considering improving our models by augmenting these Bondi solutions with radiative heating and cooling, because the planet and the associated accretion shock can be quite luminous. So if we go back to the original Bondi picture, but we start adding in the effects of radiation, we can make some sort of changes and updates. In particular, we update the energetics. We're no longer using sort of an adiabatic equation of state. We're now saying that the gas entropy can be affected by the radiation through some luminosity. And so that changes the quality of the solution. And so imagine changing the entropy of your gas. Imagine also changing the sound speed of your gas. That will then change the Mach number. And so sort of what happens is when you put radiation into these solutions, you perturb the classical Bondi solution sort of one way or another. And that'll push the sonic point inwards or outwards. And in this case, it pushes it inwards, and you'll get some sort of lower accretion rate. And this added level of complexity you get by adding radiation also gives you now additional dimensionless parameters, which you can study. And so just in terms of the radiation, you introduce some sort of opacity, optical depth, luminosity, and then there's also a characteristic cooling time. So really the name of the game in sort of this radiation Bondi situation is let me construct sort of steady state solutions and ask, how does the mass accretion rate change with sort of these fundamental radiative parameters? How does it change with the opacity, luminosity, and cooling time? And so we've done that. We've surveyed sort of these 3 parameters, and here I'm showing some subset of those results. So here I've taken a fixed cooling time, but I'm looking at the variation in optical depth and luminosity. And I parameterized this in terms of the accretion rate relative to Bondi rate. So anything less than 1 year is a suppressed accretion rate, and anything larger than 1 is a super adiabatic accretion rate. And sort of the interesting thing about this plot is that as you go to high luminosity or high optical depth, you see sort of a large suppression in the accretion rate relative to the adiabatic Bondi rate. So that's kind of a fundamental result of these models, and we can hope to apply these to the planet forming scenario. So now what I've done here is I've taken some fiducial protoplanetary disk model, and at each radius in the disk here along the x-axis, I picked a point, put some Earth mass or some planet mass in the disk, and calculated those dimensionless parameters. With those dimensionless parameters in hand, I then know F accretion, and I can plot sort of how this accretion rate is distributed relative to the Bondi rate. So what I see is this general trend that as you go interior in your protoplanetary disk, your accretion rate is suppressed just by the effects of radiative feedback. And so here, at least interior to 10 AU, we see sort of a suppression on the order of 1 to 2 magnitudes in the accretion rate. And this is just with the addition of sort of radiative feedback from your hot planet. So with that, kind of provide my summary. we can and should update our formation models with the effects of radiation. We see that radiation suppresses accretion at high luminosity or opacity. And in particular, this is a 1 to 2 order of magnitude effect for planets interior to 10 AU. So if you're interested in this work, keep your eyes out. We plan to submit this shortly, and then we'll provide sort of the entire slew of accretion rates for anybody else. So with that, I'll take a question or two.
So, in terms of the effects of radiation, what has the field been doing for that question? Or are you into listening?
That's a good question. There was actually a lot of work, I guess 40, 50 years ago now, doing this exact question for black holes. And in that case, sort of the state of the gas is radiation pressure dominant. And so you don't care about gas pressure. And so there's a lot of work, sort of, put one example here, of people looking in these black holes. And as this relates to my work, they say much more difficult work would have to be done before we can claim an equally solid understanding of the non-adiabatic gas pressure dominated solutions. So for 50 years, we've kind of really well understood the pressure or the radiation dominated regime. But it seems that that's not necessarily the case for the gas pressure, particularly because planets are just forming in these really cold environments.
Would you be interested in running a short workshop on how to apply your grid models?
Sure. Yep.
Because we can do this locally here.
Yeah.
You know, invite people over Zoom.
Yeah. And the code for actually running these models is something like 500 lines of Python. So it's like
Sweet.
really easy to get a hold of.
Nice.
Okay. I think let's take Avery again. Sorry. I'll make noise.
My name is Griselda Arroyo-Chávez. I'm a postdoc at Stewart, and I use essentially numerical simulations to study angular momentum in molecular cloud filaments. I only have 7 minutes, so I would like to make it more memorable. So if you have this symbol, we're going to have a poll. So please don't be shy, raise your hand. I'm not going to judge you. So just to practice, so how dogs should wear pants. So please raise your hand if you think that would be in this. Well, raise your hand if you think it would be this. Great. I'm going to talk about 3 projects, and I'm going to give you one slide for context. Then we're going to have a poll, and then I will tell you what I know, which is but the first project I'm working on is about the angular momentum transport in molecular clouds. People have measured velocity gradients in molecular clouds that can be interpreted as rotation. I know it's just one possibility. But we know that during the gravitational contraction and fragmentation of molecular clouds, we are losing some angular momentum. So what is the mechanism that is removing that angular momentum in moving parts? So imagine a cloud in an interstellar medium rotating. What would you use to stop that rotation? Would you use magnetic fields? Would you use gravitational torque? Would you use turbulence? We know that molecular clouds are turbulent. Would you use pressure gradient torques? So knowing only that, please raise your hand if you think we can stop that cloud using magnetic fields. Okay. Gravitational torques of gravity. Okay. Turbulence. Wow, okay, that's good to know. And pressure gradients. Okay, great. Well, if you go to the literature, gravitational torques is the favorite one. But I can define a numerical sample of clumps in my simulations and measure those torques. And here is the histogram of the magnitude of each torque, just is the color. And just divided in the density threshold that we used to define the Coulombs, but essentially in magnitude, the one that we call hydrotorque includes turbulent viscosity tend to be larger compared to. And this is not new, but I don't know anything about turbulent. The second one, I define a numerical sample of clumps and I plot those clumps in the JR relation of the angular momentum versus radius. There's a clear observational trend that he represented with the white line. But then I find some clumps do not follow the observational relation and looked at those clumps and I found that they were filaments. So I removed those filaments and then I recovered the observational trend. So what is happening with filaments? Filaments are rotating. How do filaments rotate? Do you think a filament should rotate respect to the main axis? Do you think a filament is rotating respect to a single point? Because for my clumps, they measure the angular momentum respect to the center of mass. Would you think filaments are not rotating, but they have some center of rotation? So, oops, please raise your hand if you think filaments should rotate respect to the main axis. Okay, respect to a single point. Okay. And not rotating, but have few centers of rotation. Okay, cool. Well, what I know, there's only a few examples about measurements of angular momentum in filaments. For the velocity gradient, apparently they are rotating respect to the main axis. So congratulations, you hate respect to the main axis. But apparently when they're young, so when they go through star formation process, then we move now to having some center of collapse. The thing is, how can I measure angular momentum for filaments in my simulations? I have no idea. I'm still working on that, so if you had an idea, welcome. And the last one, I'm working on the alignment between posterior outflows and filaments and where they form. And I found two different theories about I can predict that alignment. And the first one, imagine you have a filament and you have longitudinal flows due to gravity, but then you have an offset, and due to this offset, then you impart some rotation. So the thing is rotating like that. So the angular momentum vector, or in this case, the outflow should point like perpendicular. In the second one, you have the filament, and the filament is for me is formed through shocks. The shocks impart some initial rotation to the filament respect to the main axis, and then you have inside cores or clumps that inherit the rotation from the filament, and then the outflow is parallel. So please, would you think it's more probable to have perpendicular alignment? Please raise your hand. Okay. Oops, parallel. Okay, what I know. Well, if you go to the different surveys of what people have observed, they find there is mostly random or perpendicular, never parallel. So it's not parallel. It's mostly random for a few examples where they're perpendicular. The perpendicular means the side is parallel, random. What I'm doing now is identifying filaments in my simulations. What I have found so far is that in 3D, they tend to be perpendicular, but when I project those angles in 2D, then they tend to be random. So something that in 3D is perpendicular could be random in 2D projections. And we are looking at the evolution, not just its time, just evolution. And that's all.
Can you say a little more about how you measure the hydrodynamic or the turbulent torque in these core scales?
Yeah, I took the momentum equation for fluids. Essentially, you have all of the contributions, the gravity term, the pressure gradient, the magnetic torque, and the hydro that comes from the advection term. And then we do R cross P, essentially taking P as the momentum equation for fluid. So you have R cross P, the angular momentum. And then every term I can transform it to per unit mass. So when I'm using SPH, so I can measure these torques for every particle in 5 coulombs and zoom over the particles, or you can do that for fixed volume if you have like a mesh code. So it depends. So knowing the particles that belong to every clump, I can zoom over the contribution.
But the viscous term, are you using like a,
Oh, okay.
how do you get a viscosity? in
Yeah,
that?
the viscosity is tricky because it doesn't mean like I put in a viscous term. It's not that viscous term. It's the angular momentum being transported by the fluid itself. It's a property of the fluid, while viscosity is the turbulent viscosity is a property of the flow, while viscosity, this microscopic viscosity, is a property of the fluid. So we are not adding an extra viscous term. It's been done by the flow itself. That's the idea. Don't believe me. I'm not sure.
Helping it. You can see here, it is still tracking to. Amber is kind of and top of the other one. Yes, that's the line. Okay. Yes, this line. And I'll wait at you when you're thinking. Oh my gosh. Okay, I'm just gonna hold this. Can people hear me? Yes, okay. Okay, yes, so I'm Joe Adamo. I'm a 5th year grad student in Sphere Observatory in the AZ Cosmo Lab. And we have to be talking about something totally different on very much larger scales. We're using machine learning to accelerate inference for SPHEREx. So what exactly are we talking about here in terms of science? So we're looking at cosmic inflation, and more specifically one of the tracers of inflation, which is known as primordial non-Gaussianity. And that is just referring to the degree to which the initial matter density field is expected to deviate from a Gaussian distribution. And the very short version is that different theories for cosmic inflation will predict different amounts of non-Gaussianity. So for like single field slow roll inflation that people usually learn about in school, there is either no non-Gaussianity or it's very small, less than 0.01. For more complicated multi-field inflation models, it's greater than 1. And as it stands right now, our best measurements are not able to differentiate between these. But if we can differentiate, like if we can get a value uncertainty of around 1, we can hope maybe say, okay, maybe multi-field inflation models are not thing. So and the reason we're interested in this, at least in late time, is so these early deviations here can propagate to the late time matter distribution. So you can see these are 2 simulations run with FNL equals 1000 and FNL equals 0. So very very dramatized, but that's kind of the idea. So enter the spectrophotometer for the history of the universe epoch of reionization and ICES Explorer, which is hard to remember. So this is a NASA MidX mission that launched in early March. That's a picture of a live stream of the telescope in space. As I just said, it's an infrared telescope. It's going to be all sky, and we actually already have data. I don't know if the video will play. No, it will not. But so this is supposed to be a video of NGC 1760 with a bunch of different filters flying by. So we're already getting data. It's nominally a 2-year mission. But why do we care about this? So SPHEREx is going to be trying to constrain FNL to around 0.5 or 1, depending on who you ask, by analyzing the galaxy power spectrum and bispectrum at ultra large scales, which we're able to do because it's an all sky survey. And so this kind of differentiates it from other spectroscopic surveys like DESI. And on this right plot, you can see some forecasted constraints. So the blue circle is from Planck, which is currently our best a measurement for FNL, and we're trying to get to potentially the other circles. So that's the very high level plan. So how are we actually going to get to do that? So in order to prepare for the full analysis, we need to run a lot of simulated analyses to study various things like how do your priors on parameters affect your constraints? What types of scales do we need to include, or where does it like get too difficult to model? And like what various other things like the covariance matrix, if you know what that is. So the problem with this is that these analyses take a very long time because each step of your MCFC chain, you have to run a Boltzmann solver, and you have to vary quite a few parameters. So these take a very long time to run. So this is where my goal comes in, to use a neural network emulator to emulate the observable, in this case, the galaxy power spectrum, to speed this up. And this is joint project with an undergrad, Grace Gibbons, who has been involved with Time Step, and Annie Moore, who's from physics grad student. So more specifically, what I built was, this should say 4 million, not 2 million. So I generated a training set of 4 million galaxy power spectrum multipoles predicted by what's known as the effective field theory of large scale structure. This is the clean equation version of the equation that is like predicts this thing. So this is I used previous postdoc from our group named Yosuke Kobayashi, his code to generate these. I did specific multiple moments that are expected to have the most signal involved. And in this particular analysis is going to be what's known as multi-tracer. So you're analyzing multiple galaxy samples at the same time. And so I've picked, just as a proof of concept, two galaxy sample tracer bins and two redshift bins. And I'm only emulating part of the model, which is in this yellow circle or square here, because the other terms are pretty quick to calculate, so you don't need to do that. Okay, so now moving on to the emulator architecture, I'm going to speed through. I could talk for an hour about this thing. So at the very high level, the network I built is very modular. So each specific sample or redshift bin are totally independent. So these are trained independently. They don't talk to each other at all. And I'm working with correlated tracer bins, which means I have 6 networks in total. And each one of those has a fully connected, more traditional type network, and then a transformer at the end, which is the new fangled fancy machine learning thing. ChatGPT uses transformers, and they've been shown to work for emulators like this. And this whole thing has been trained using a method called stochastic gradient descent to minimize the delta chi-squared between the training set, like the truth, and whatever the emulator outputs. And the specific hyperparameters used are have been optimized by Grace. That was her sub-project in here. So moving on to actual results. So if you look at this is the important one, this great thing. So we get a delta chi-squared median of about 0.35, which matches other emulators in the literature. So we're doing really well. If you look at this right plot, which is you can see the delta chi-squared across the parameter space that I trained this on. I trained this on within lambda CDM, so all 5 lambda CDM parameters and a few galaxy bias parameters. But so you don't see any regions where we're performing worse or better, which is good. There won't be any biases there. And the real money plot is you can actually run chains with this. So this so the gray one is run with the actual analytic code, and the blue is run with my emulator, and you can see they line up almost perfectly on top of each other. The biggest difference, the time. So the analytical chain took over a week on my laptop versus 4 hours with my emulator. So you can really see the improvement in wait time there. And these are just some statistics on how we're doing comparing the two chains together. So we're doing quite well, I would think. So we're moving on from here to actually starting to use this to run impact studies with SPHEREx. So I'm just going to leave my summary up because I think I'm out of time. I do want to mention my code is on GitHub if you want to try using this yourself. It's pip installable, lots of good documentation on there, and there should be a paper coming out soon. So thank you.
Yes, Joe, thanks for the great talk. So at what redshift range is this the most sensitive to being able to get out this non-Gaussianity signature?
So it's mostly we're looking at like lower redshifts, mainly because like when you get to, I believe when you get to higher redshifts, the volume goes down. So you really want like the largest scales possible. If you're asking about the specific emulator, so this can be applied to like any range you want. But yeah, SPHEREx, I think SPHEREx is going up to like redshift 2. I think that's right.
Apologies if I missed this, but could you say a little bit more about where your training data is coming from? Is this all based on like an n-body simulation sort of?
Yes, so this is all like a theoretical model based on something called the effective field theory of large scale structure. So it allows you to predict the galaxy power spectrum using just essentially very complicated math.
Oh, it's analytic.
Yeah, it's all
Oh,
analytic.
okay.
You could use simulations if you wanted, but then you run into like you don't have enough training samples. But that's something I'm interested in potentially looking at later. So, okay, let's go with that.
Our next PPR is going to be technique.
I'll wait about 4 minutes in.
Hi, remember me?
Oh, sorry. Lead on.
Hi everyone, I'm Haley Bowden. I'm a 6th-year grad student in the astronomy department, and I am interested in the properties of dark matter halos and how the properties of the dark matter halo impact the galaxy that it hosts. And this can be a bit of a challenging thing to probe because we can't really directly measure the properties of the halo. And so we need a way to connect what we can measure to what we want to know. So to restate, our problem is we want to understand the properties of the dark matter halo, but we can't observe them directly. They should be related to the properties of the galaxies that we're observing, though. And so what we want to do is learn the mapping that is necessary to go from the halo properties to the galaxies that we observe. So you might see this in a simulation where we would take a dark matter only simulation and we'd have our a parameter set describing our dark matter halos. In this case, I've chosen halo mass, halo concentration, or in other words, like how concentrated the mass is towards the center versus more spread out. And the accretion rate is the halo gaining or losing matter and at what rate averaged over a long period of time. And in a simulation, what we might do is figure out how to put galaxies in these halos such that we reproduce the universe as observed. And what I'm looking to do is the opposite. Say, given an observation of a galaxy or a catalog of galaxies, how do we put constraints on the halo properties? And if we trust our simulation, this kind of comes down to just a Bayes theorem problem. We have the properties that we want to learn, which I have here as theta, given our observation. We just use a simple prior, and we have from our simulation the probability of an observation given our halo properties. So as a simple case study in how this works, we have the stellar mass halo mass relation. So it's well understood that the stellar mass of an object is tied to the halo mass of the mass of its host dark matter halo. And this relationship between stellar and halo mass has been studied quite a bit, and a lot of thought has gone into what is this relationship and how much scatter is there in this relationship. And so from that, we can say if we know the stellar mass of our galaxy to within a certain uncertainty, we can use our understanding of this relationship and the scatter in this relationship to get a pretty good idea of what our halo mass is and what our uncertainty on that halo mass is. Things get more complicated when we don't have a one property to one property relationship that we are trying to do. So in my case, what I'm trying to use is the properties of a galaxy and a description of what kind of neighborhood the galaxy hangs out in. So the here I'm showing like the distances to the galaxy's nearest neighbors and the properties of those nearest neighbors. I want to take all of that information and extract what is relevant to halo mass, concentration, and accretion rate. What I do is I use a technique called simulation-based inference, where I have a simple prior for my halo properties, and I am using machine learning to learn a transformation that to go from this prior to a posterior conditioned on our observable. So I have a bunch of simulated observables. I have a whole galaxy catalog that is simulated, and I want to, and I'm training this transformation such that if I go to a high likelihood place on my posterior, it should give me a sample that is consistent with my observation. If I go to a low likelihood space, it should give me a sample that is inconsistent. So we iterate over this catalog until we train this posterior. So as an example, this is one of the galaxies in my catalog, and I, because it is a simulated catalog, I know what the truth is. The truth is this white line. Sorry, it's a little bit small. And in orange, you can see our prior, or this is just the distribution of all of the halos in our simulation box. And in blue is the posterior. This is the output from our model telling you, given our observation, this is the kind of constraints we can put on the halo mass. So this is very, this is, you know, on an object where we know the truth. But if we were to go to an observed catalog, like we would like to do, then we will be able to place constraints on the properties of the host halos of the galaxies that we observe. And yeah, this is just a quick summary. Trying to infer halo properties that we can't directly measure, using machine learning to learn what the properties of the host halo are for a given observation, and to also learn the uncertainties on those halo properties. That's cool. Thank you.
Thank you, really great talk. Could you say a bit more about how, where are you getting your priors from? Because they don't seem to be elementary distributions. It seems that they're motivated by something.
Yeah, let's go backwards. Yes, so in this case, my prior is just the distribution of all of the halos in my simulation box. So this is just, these are all of the masses it could be. And this is what, so yeah, I'm assuming that my simulation box is covering this full range. Yeah, you can assume a simpler prior, but by training it on my catalog, unless you reweight things, that is how it goes.
Is it a quick question?
You can decide not to answer it, but for the hard question, how do you have a constraint on what reality is and whether or not the neural network you train on your simulations has the same underlying correlations as the universe?
Yes, so that's a very good question, perhaps the most important one. Yeah,
Not a good short
so,
question, so.
so the, I would say that it is perhaps more accurate that we are training an observable that is sensitive to these halo properties than we are getting direct constraints on these halo properties. We try to limit ourselves to observables that are well simulated. We're using fairly basic things, but yeah, it's the change of domain going from the simulation to the real universe is always going to be an issue.
Our next and last speaker for today is Eonho.
Can everyone hear me okay? Okay. Hello, my name is Eonho. I'm a 6th-year grad student in applied math. And I'm going to talk about a project I worked on over the summer about exoplanets and dust. Before I do that, though, I want to talk a little about what I usually do. I'm a big hydrodynamics fan. In the planet formation context, this is a movie that I got. Please imagine planet moving in the disk and carving a gap. And they are gonna launch vortices in the disk, interacting with the, right, because of planet interacting with the disk. And these vortices appear as these non-axisymmetric features in observations. So studying these vortices are important. Like if you know when these vortices form, you can back out important information, useful information about the disk when that formed the vortices. And you can also study how vortices affect planet migration, so that controls where planets are going to end up eventually. That's what I usually work on. But let's talk about exoplanets and dust. So the key idea behind this project is that dust hangs around planets for a while from the formation phase to accretion, and even after the gas disk has dissipated, debris disk. We're going to focus on this debris disk phase for this talk. And why debris disk? There's something interesting going on here. That you have these big rocks, kilometer size, left over from planet formation. They collide with one another. They gradually produce these smaller size dust particles down to like 1 micron. And these smaller particles drift inward as a radiation effect called Poynting-Robertson drag. They're also called zodiacal dust. And you can look at inner solar system. They produce this mass influx of about 10 to the 8 grams per second. And you can also look at outside solar system. And about 1/5 of nearby stars have 1,000 times or more. These are actually surveys done by LBTI. You can be proud of that. So the central question of this project is that, okay, we have a lot of dust around planets. Can this dust affect the planets, and we can observe that? This is a plot you have to show in any exoplanet talk, the population. This is a mass, that is orbital period or the distance from the star. And turns out planets on the top left corner, they tend to accrete a lot of the dust that might exist. So we're going to focus on these hot Jupiters. Again, this is a movie. Please imagine as this planet moves in front of the star, passes in front of the star, you'll see a dip in the brightness curve, and you can figure out what the size of the planet is. And the size turns out to be sensitive to the atmospheric conditions. So maybe dust can do some changes in the atmosphere, and we can observe that. Here's a method slide if you care. Basically, we use a 1D model, spherical model for the atmosphere. So that gives the structure, basically temperature profile of the planet. We also use karma. This is an aerosol code that basically simulates clouds, where it's going to form, and what kind of particles are going to constitute those clouds. We're going to assume simple set of condensable species. One silicate, Mg2SiO4, another one TiO2, that's the homogeneous nucleation species. And the point of this study is imposed as an upper boundary condition. We put a mass influx of silicate, Mg2SiO4, in the simulation. And we pick a generic hot Jupiter with these parameters. We explore different infall rates. Best case, no infall. 10 to the 8 grams per second, that's the inner solar system value. And the 10 to 11, which is reasonable based on the surveys, or at least 1/5 of the nearby stars. And here's results. So the top panel is showing the vertical distribution of the clouds, where the clouds are going to fall. And the bottom one is showing the size distribution. Okay, what's the size of the dust particles constituting those clouds at certain height, basically at this dotted line. So you see this cloud bank forming at about 1 bar. And the particles have this size distribution without any infall. But if you add infall, you see that the distribution of dust cloud changes a lot vertically and in size distribution as well. This peak is coming from the input size of 1 micron. And we can also look at the spectra of these exoplanets. It's trying to illustrate here the transmission spectra. Basically, as the planet passes in front of the star, it's going to block some of the light. Some of the light is going to get attenuated by the atmosphere. And if you have a cloud deck high up in the atmosphere, it's going to block out more light than it would otherwise. And that's what we see in our simulation as well. You do radiator transfer calculation, and the green is when you have a lot of infall, 10 to the 11 grams per second. That has different spectra from other cases. No infall, and 10 to the 8 value. Those are practically indistinguishable. So basically you get these muted spectral features when you have these high infall. And basically that's it. And the idea is that dust accretion can change planet cloud distribution and spectra. We make the prediction that if you have hot Jupiters in dust systems, what means dusty, 10 to 11 grams per second, then you're going to have transmission spectra with muted features. But apparently we don't know any of these systems, so it might be interesting to observe one and test this hypothesis. And I did not talk about it today, but we also apply this framework to more further out planets that are more massive, or basically ones you can detect with direct imaging technique. Similar story there. This infall can change the temperature profile of the planet by providing additional positive feedback. And then it can also redden the emission spectra of those planets. Thank you, and I'll take any questions.
Before questions, a reminder to the speakers of not run away for a group picture. No question.
So the dust can be charged, right? And perhaps there could be effects from electric and magnetic fields. Could the magnetic field of the planet affect your results?
That's a good question. I guess in the case of Earth's magnetic field protect us from sun's high energy particles. So I guess that could change the accretion. I guess especially if you go to inner stellar system, where the temperature gets high and these molecules get dissociated. That is not something we considered here. They're all neutral, but that is a very interesting question.
Really over time by 1 minute, so there are no more questions. Let's take a look again and all the